Conflicting study findings can be confusing. Some interpret these disagreements as evidence that science is subjective, shaped by who conducts the study or how results are presented. A clear example emerged during the COVID-19 pandemic, when multiple studies evaluated hydroxychloroquine as a treatment. They appeared to ask the same question: does hydroxychloroquine improve outcomes in COVID-19? But their findings were very different. An observational study reported higher rates of viral clearance among treated patients, suggesting a potential benefit. In contrast, the recovery trial, conducted by Horby and colleagues and published in the New England Journal of Medicine in 2020, found no reduction in mortality and no clinical benefit. At first glance, this appears to be a contradiction, but it suggests that something important differs between the studies. This leads to the central question for this video: why do studies report different findings, even when they appear to address the same research question? And more importantly, how do we evaluate these differences and decide what conclusions to draw? This issue became especially visible during the COVID-19 pandemic, when the literature was filled with conflicting results. Anthony Fauci emphasized that scientifically robust and ethically sound research is essential for reliable conclusions. The implication is straightforward: if the design and execution are not rigorous, the results may be misleading. Differences in study findings have real consequences. They influence clinical decisions, public health policy, and how evidence is interpreted. I'm Jose B., the traveling medical data scientist. In this video, we examine why studies that appear similar can lead to different conclusions and how to evaluate those differences in a structured way. At a high level, differences in study findings arise from two sources. They may reflect systematic differences between studies. These differences may arise because the studies are not asking the same question, or because they differ in design, conduct, or analysis. Or they may reflect random variation, where studies address the same question but yield different results by chance. This distinction is critical. A fundamental reason studies differ is the research question itself. Even small changes in what is being asked can lead to different conclusions. To make these differences explicit, we use the PICOT structure. This defines the research question in terms of 5 elements: P, population, who are the participants; I, intervention, what is being done or given; C, comparison, what is it being compared to; O, outcome, what result is being measured; T, time, over what period is the outcome assessed. If any of these elements differ, the studies are not answering the same question. Consider 2 randomized trials of the Pfizer-BioNTech COVID-19 vaccine. Polak and colleagues studied adults, while Walter and colleagues studied children. Both used the same vaccine, the same comparator, similar outcomes, and similar follow-up. So intervention, comparison, outcome, and time are aligned. Strictly speaking, this means the studies are answering different questions because the target populations differ. However, the results are consistent. Polak and colleagues reported about 95% efficacy, while Walter and colleagues reported about 91% efficacy. So these studies do not conflict. They provide consistent evidence across related but distinct populations. Now consider the recovery trial. The intervention, comparator, outcome, and follow-up are the same across patients. What differs is disease severity at baseline. Among patients requiring mechanical ventilation, dexamethasone reduced mortality. Among those not requiring oxygen, there was no benefit and a possible signal of harm. Even within the same study, changing the population changes the answer. Population is only one source of variation. Consider 2 randomized trials in patients with atrial fibrillation. The Aristotle trial compared apixaban with warfarin. The RELY trial compared dabigatran with warfarin. Across these studies, population, outcome, and follow-up are similar. What differs is the intervention. Apixaban reduced both stroke and major bleeding. Dabigatran showed dose-dependent effects with a different bleeding profile. Changing the intervention changes the conclusion. Another source of variation lies in the choice of comparator. Consider trials of statin therapy in patients with coronary disease. In the Scandinavian simvastatin survival study, simvastatin was compared with placebo and produced a large reduction in mortality. In the Prove-It-TIMI 22 trial, intensive atorvastatin was compared with standard dose pravastatin. In that setting, the magnitude of benefit was smaller. These studies differ in more than just the comparator, including population and follow-up, but they illustrate an important principle. When the comparator changes, the effect size can change. Another source of variation lies in how outcomes are defined. Even when the population, treatment, comparator, and design are the same, changing the outcome can change the conclusion. Consider the ACCORD trial, published in 2008. The primary outcome was a composite of non-fatal myocardial infarction, non-fatal stroke, or cardiovascular death. Using that composite outcome, intensive therapy did not show a statistically significant benefit. But when the outcome is defined as all-cause mortality, the conclusion changes. Intensive therapy was associated with a significantly higher risk of death. So even within the same trial, changing the outcome definition can shift the conclusion. A related issue arises when surrogate outcomes are used in place of clinical outcomes. In earlier studies of antiarrhythmic therapy, such as the EFSVA trial, incanide and flecainide effectively suppressed ventricular arrhythmias, a surrogate outcome. In contrast, the cardiac arrhythmia suppression trial, conducted in a similar population, evaluated mortality as the primary outcome. In that trial, the same drugs were associated with an increased risk of death. So when the outcome shifted from a surrogate to a clinical endpoint, the conclusion reversed. Another dimension that can alter conclusions is time. Some treatment effects emerge only after longer follow-up. For example, in type 2 diabetes, the ACCORD trial, with a median follow-up of 3.5 years, did not show a reduction in major cardiovascular events and was associated with increased mortality. In contrast, long-term follow-up from the United Kingdom prospective diabetes study showed reductions in myocardial infarction and all-cause mortality over time. This illustrates that conclusions can depend on when outcomes are measured. Now consider another example. The TIMI-3B trial found no clear benefit of an early invasive strategy. Several years later, the Tactics TIMI-18 trial showed a clear benefit. At first glance, this appears to be a contradiction, but the research question and study design are similar. What changed is the clinical context. Between these trials, major advances occurred in standard care, including coronary stents and improved antiplatelet therapy. So the difference reflects changes in the clinical environment over time. Even when the research question is aligned, studies can still disagree. This points to another source of variation: study design. In observational studies, the investigator does not assign the exposure. As a result, groups often differ at baseline, leading to confounding. Because of this, observational studies can identify associations, but they do not, on their own, establish causation. In contrast, interventional studies assign the exposure, often using randomization to create comparable groups. This improves internal validity and strengthens causal inference. Large observational studies once suggested that antioxidant use was associated with lower risks of cancer and heart disease. For example, observational analyses, such as those from the Nurses' Health Study, found lower cardiovascular risk among vitamin E users. These findings led to widespread use. But randomized trials did not confirm this benefit, and in some cases suggested harm. In the Heart Outcomes Prevention Evaluation trial, vitamin E supplementation did not reduce cardiovascular events. Trials of beta-carotene also suggested harm, particularly among smokers. So the issue is not simply that studies disagree. It is that even when the research question is similar, different study designs create different comparisons, and those differences can lead to different conclusions. Design shapes how comparisons are made, but it does not, on its own, determine the results. Even studies with similar designs can produce different findings. These differences often arise from how studies are conducted and analyzed. Data collection, follow-up, handling of missing data, and analytical choices can all influence the final estimate. As a result, studies that appear similar may still reach different conclusions. Now consider blinding. Blinding determines whether patients or outcome assessors are aware of the assigned treatment. This is especially important for subjective outcomes such as pain. In the VERTOS-2 trial, vertebroplasty was compared with conservative therapy. Patients were not blinded, and the procedure appeared to reduce pain. In contrast, in the trial by Bookbinder and colleagues, vertebroplasty was compared with a sham procedure. Patients and outcome assessors were blinded. In this trial, there was no meaningful difference between groups. The key point is that the sham-controlled, blinded design accounted for expectations. So the difference in findings reflects both the use of blinding and the choice of comparator. When expectations were controlled, the apparent benefit was not observed. Study conduct across sites is particularly important in procedural trials, where outcomes depend on operator skill and experience. Two randomized trials illustrate this, EVA3S and CREST. In the EVA3S trial, stenting was associated with a higher risk of stroke and death. In contrast, the CREST trial found no significant difference between the two strategies. Both trials addressed the same clinical question using a randomized design. What differed was how the procedures were performed across sites. CREST required rigorous operator training and certification, whereas EVA3S included sites with more variable experience. Differences in operator skill and site experience likely contributed to the different findings. But variability does not end at data collection. Even when conduct is comparable, different analytical choices can lead to different conclusions. The PRAISE-1 and PRAISE-2 trials illustrate this point. In PRAISE-1, a post-hoc subgroup analysis suggested that amlodipine reduced mortality among patients with non-ischemic cardiomyopathy. However, when this same question was specified in advance and tested prospectively in PRAISE-2, the benefit was not observed. The data did not fundamentally change. What changed was the analytical approach and the timing of the hypothesis. This highlights a key principle. Analyses defined after examining the data are more prone to misleading conclusions. Consider another example. Paroxetine Study 329 was a randomized controlled trial evaluating the efficacy and safety of paroxetine in adolescents with depression. The original analysis used methods such as last observation carried forward to handle missing data and concluded that paroxetine was effective and safe. Several years later, Lenori and colleagues reanalyzed the same dataset. Using more appropriate methods to handle missing data, the reanalysis reached a very different conclusion. It found no evidence of efficacy and identified important safety concerns. The data and the research question were unchanged. What differed was how missing data were handled, and that alone led to a different answer. Here is another example of how analytical choices can affect conclusions. A 2001 study by Rettelmeier and Singh, published in the Annals of Internal Medicine, reported that Oscar-winning actors lived about 4 years longer than their peers. However, a 2006 reanalysis showed that this result was driven by immortal time bias. To win an Oscar, an actor must survive long enough to receive the award, creating a period during which death cannot occur. The original analysis counted this time as survival for winners, inflating their apparent advantage. When this bias was addressed using time-dependent methods, the survival difference was much smaller and no longer statistically significant. The examples we have discussed may seem different, but they reflect a common underlying issue: bias. Bias is systematic. It pushes results away from the truth. At a deeper level, differences in study findings arise from only two sources: bias, which is systematic, and chance, which is random. So far, we have focused on systematic differences between studies, including the research question, study design, conduct, and analysis. But even when these factors are aligned, results may still differ. This leads to the final explanation: random variation. Even well-designed studies are based on samples rather than the full population. As a result, estimates vary from study to study simply due to chance. Even when studies are well-designed and address similar questions, their findings can differ due to random variation. This occurs because we observe only a sample, not the entire population, so estimates fluctuate from study to study. This variation is more pronounced in smaller studies, where estimates are less precise. Consider trials of intravenous magnesium in acute myocardial infarction. Early, smaller trials suggested a reduction in mortality. For example, the Limit 2 trial reported a mortality benefit. However, in larger trials, such as ISIS-4 and MAGIC, no mortality benefit was found. These studies evaluated the same intervention and outcome in similar clinical settings, but differed in sample size and precision. The apparent benefit seen in smaller studies was not confirmed in larger trials. The key point is simple: chance alone can lead to different findings. Now that we have seen the range of reasons why studies report different findings, let's return to the 2 hydroxychloroquine studies from the beginning. Why were their results incompatible? At first glance, the population and intervention appear similar, but the comparison differs, the outcomes are not the same, and the time frames are different. These studies are not answering the same question. This is the first explanation: differences in the research question, as defined by PICOT. Second, the study designs differ. One is observational, where treatment is not assigned by the investigator. The other is a randomized controlled trial, where treatment is assigned. These designs create fundamentally different comparisons. Third, differences in conduct and analysis may also contribute, including how outcomes are measured and how the data are analyzed. Finally, even when everything is aligned, random variation can still play a role. So the disagreement is not a contradiction. It reflects differences in the question, the design, the analysis, and chance. In evidence-based medicine, studies are often organized into a hierarchy of evidence. In general, observational studies provide weaker evidence, while randomized trials and meta-analyses provide stronger evidence. So when studies disagree, it is tempting to trust the study higher in this hierarchy. And often, that is a reasonable starting point. But it is not a rule. Study quality, conduct, and relevance also matter. A poorly conducted randomized trial may be less reliable than a well-conducted observational study. So the goal is not simply to rank studies. It is to understand how the evidence was generated and what question each study is truly answering. Today's takeaway is straightforward. Studies do not disagree at random. When findings differ, it is usually because something differs between the studies. This is not an exhaustive list, but the reasons can be grouped into 4 broad categories. First, the research question may differ. Even small changes in population, intervention, comparison, outcome, or time mean the studies are not asking the same question. Second, study design may differ. Observational and interventional studies construct fundamentally different comparisons. Third, differences in study conduct and analysis can affect results, even when the question and design are the same. Finally, even when everything is aligned, random variation can still lead to different findings. When studies disagree, the goal is not to choose a side arbitrarily. It is to identify what differs, why it differs, and which result is more trustworthy. We can approach this systematically. Start by asking whether the studies are answering the same question. If they are, consider the level of evidence. Prefer the study with higher level evidence. If the level is similar, examine conduct and analysis. Prefer the study with better execution. If the studies remain similar, consider precision. Prefer the study with more precise results. If precision is also similar, the evidence is uncertain. Interpret the findings cautiously. Even after this structured evaluation, one final question remains. Do the results make sense biologically, and do they align with clinical experience? Biological plausibility does not determine study results. It helps us interpret how credible those results are. Clinical judgment plays a similar role. These do not replace evidence. They help us decide how much confidence to place in it. Now let's apply this idea to a quiz. Consider 2 large randomized trials evaluating beta-carotene supplementation. In the ATBC trial, conducted among male smokers in Finland, beta-carotene supplementation was associated with an increased risk of lung cancer. In contrast, in the Physicians' Health Study, conducted among male physicians in the United States, beta-carotene had no significant effect on cancer risk. Both studies were randomized, double-blind, placebo-controlled trials evaluating the same intervention, yet they arrived at different conclusions. Why did these 2 well-designed randomized trials produce different findings? Pause the video if you need time to think about your answer. The correct answer is B, differences in population and baseline risk. Both studies were well-designed randomized trials evaluating the same intervention, but they did not study the same population. In the ATBC trial, participants were male smokers, a high-risk group for lung cancer. In the Physicians' Health Study, participants were mostly non-smokers, with much lower baseline risk. When baseline risk differs, the effect of an intervention can also differ. The same treatment can appear harmful in one population and have no effect in another. So the difference in findings is not due to chance alone or flaws in study design. It reflects a fundamental difference in who was studied. This is why aligning the population is critical when comparing studies. If medical research ever becomes perfectly consistent, don't feel reassured. Feel suspicious. As the title of this channel suggests, I'm a traveling medical data scientist. Today, I'm sharing footage I captured in Cholula, Mexico. The church you see in the distance is the Iglesia de Nuestra Señora de los Remedios. Even at night, it stands out, illuminated and elevated above the rest of the city. It's a 16th century Spanish colonial church built on top of the Great Pyramid of Cholula. What appears to be a simple hill carries a much older structure underneath it. The church, completed in 1574 and later rebuilt, reflects a moment in history where one system was placed directly over another. So what you see is only the surface. That idea carries over to research. When studies report different findings, it often means something differs beneath the surface, not that one is simply right and the other is wrong. That's all for today. Thanks for watching. This is Jose B., the traveling medical data scientist, signing off.